Okay, but there is something that can go wrong sometimes. Uh, Here's another example of a matrix. Let me just give you a heads up on what can go wrong. What if you are reducing this matrix and at some point you come to the conclusion, hey, this is not going to be possible to turn this into the identity matrix. Because remember, the reduced row echelon form of every square matrix is not going to always be the identity. Sometimes it might be something else. And in which case, well, then that just means the matrix doesn't have an inverse. So that's also uh, useful information. And in that sense, the algorithm that we just introduced, it will still succeed in that case, just in the sense that however disappointing this may be, you'll have to draw the conclusion that the matrix doesn't have an inverse. Okay, so let's work on this matrix. By the way, this doesn't just work for 3 by 3 matrices, right? This matrix happened to be 3 by 3, so when we adjoined it with the identity, we used the 3 by 3 identity. So if you had say a 6 by 6 matrix that you wanted to find the inverse of, you'd put that 6 by 6 matrix here, and then you would put the 6 by 6 identity matrix here. So that you can do this at any level of complexity, no matter how large your matrix is, as long as it's square, of course. But both of these examples just are for the 3 by 3 case, because to be honest, it's already complex enough with 3 by 3 matrices. As soon as you get up into 4 by 4 matrices, unless they're artificially constructed just to make things work out nicely, it can already be really rough working with a 4 by 4 matrix. Anyways, okay, I'm digressing. Let's move on to part B here. So we've got our matrix M, which is given by 1, 6, 4, 2, 4, negative 1, and then negative 1, 2, and 5. Okay, now I can scroll up and we'll adjoin this with the 3 by 3 identity matrix, and we'll start finding the inverse. So notice that you don't wait until you know there's an inverse to start looking for the inverse. You kind of start your search for the inverse at the beginning, and then if it fails, well, then it fails. But if it succeeds, then at the end, you'll already have found the inverse, and you won't have to start looking for it once you find out there is an inverse. Okay, let's start reducing this matrix. These need to be zeros. So let's take row 2 and replace it with row 2 minus 2 row 1. And then row 3 will be replaced with row 3 plus row 1. Okay, so what's that going to give us? Oops, what's going to change? So row 2 and row 3 are both going to change. So what's going to happen to row 2? We're going to subtract row 1 twice, so we'll have a 0. 4 minus 12 will be negative 8. Negative 1 minus 8, that'll give us negative 9, right? And then what else? What do we have? We'll have negative 2, 1, and 0 over here. And then for row 3, we add row 1 once, so we'll have 0, then we'll have 8, then we'll have 9, then 1, 0, and 1. And you might already be able to see what's happening and be able to predict the result here. Look at this. If you just look at the left half of this matrix construction here, we've got 0, negative 8, and negative 9, and we've got 0, 8, and 9. So, okay, what we could do is we could multiply row 2 by negative 1 over 8 and turn that into a 1. But then that's going to introduce a fraction here, here, and here. And why would we be doing that? We would turn this into a positive 1 so that we could subtract row 2 8 times from row 3. But since these numbers match up so nicely, why don't we just add row 2 to row 3 first? So, and before we worry about any 1s. So take row 3 and replace it with row 3 plus row 2. And what that's going to give us is this. We're just going to have 0, 0, 0, negative 1, 1, and 1. Okay, but focusing over here specifically, what do you see here? You see a row of zeros. As soon as you have a row of zeros that appears in a sequence of matrices when you're applying row operations to some matrix, as soon as you see a row of zeros, you can immediately stop and say there's no way the reduced row echelon form of this matrix is going to be the identity. So this algorithm is never going to succeed in producing an inverse to this matrix. What was it called? M, I think, that we started with. right? We're never going to find an inverse for this matrix. That doesn't mean the algorithm failed, because it tells you that. The fact that we have a row of zeros showing up here, that just means that we're going to stop and say, therefore, M inverse does not exist. In other words, M is not invertible. Either of those statements are saying the same thing. So those are two different options you have for wording to use. But if you're asked to find the inverse, like this one, this question said, find the inverse of each matrix if it exists, right? This part is implied. If this part isn't here, that doesn't necessarily mean that the matrix is guaranteed to have an inverse. If someone asks you to find the inverse of a matrix and it doesn't have an inverse, then fine, just tell them that it doesn't have an inverse, and that's just as good, right? That's just as effective. It's just like if I gave you an equation and I said solve it, and it turned out there was no solutions. Well, you coming back and telling me there's no solutions, that's still solving the equation, right? You're still describing the solution set, which in that case happens to be empty. So this is still successful in the sense that we determined that there is no inverse, so we know now to not bother looking. So, and then just to draw attention to this, it's this row of zeros that made us draw that conclusion. Okay. All right. So in summary, this summarizes formally what you do. So if you want to find the inverse of a matrix A, you form this construction here. You adjoin it with a copy of the identity matrix of the same size. You then perform row operations to try to turn the left half into the identity. And what you're shooting for is something like this. If you've turned the left half into the identity, then whatever consequence happened over on the right-hand side, the right half, I should say, since it's not an equation, whatever happens on the right half, that's going to end up giving you the inverse of the matrix A. And if it's impossible to get the identity here, then that means the process fails, and in that case, you will just say that A is not invertible. So it's still success in that sense. Okay, one last thing I'll point out. If you have two matrices that you know are invertible, so that's the assumptions here in this fact. If A and B are both invertible and they happen to be square and of the same size, of course they have to be square if they're invertible, because we don't talk about invertibility for non-square matrices. But the important part here is that they're the same size. So if they're the same size, you can multiply them, and it makes sense to talk about their product. It turns out that their product will also be invertible. And we can also say more. We can say what the inverse of the product is going to be. It's actually just going to be the product of inverses. And actually be careful here. If you try to do this, this is what many people would guess. You would guess that it might be A inverse times B inverse, but that won't actually work. What you need to do is take B inverse first and then multiply that on the right by A inverse. So that actually tells you a nice rule for computing the inverse of a product of two matrices. And how do you check that this works? Just check it by direct multiplication. Check that if you take A times B and multiply it by B inverse A inverse, you actually get the identity. But you do. Use the associative property to shuffle the brackets around, and you can make a point of multiplying the B and the B inverse directly, which that's going to give you the identity, right? So you end up just getting A times A inverse, which is also the identity. Let me just clarify, let me add an annotation here. This is equal to the identity. Okay, and that's why we were able to, the next step was just A times A inverse, because it's really A times the identity times A inverse, but multiplying by the identity doesn't change anything, so you can just omit it. So that gives you the identity if you multiply them in this direction, but remember you also have to check the other direction as well, so, or the other order of multiplication. So B inverse A inverse times AB, what do you end up getting? Well, do the same thing, right? Change the order in which the multiplication happens in the sense of shuffling the brackets only, right? Notice I'm not changing the order of any of the factors. Remember that. You can't move the factors around, but you can shuffle the brackets around. So because of this, again, we can say this is equal to the identity, and then the next step, we're just going to have B inverse times b. And any matrix multiplied by its inverse is still just going to give you the identity. So that's the check. That's how you can say, okay, you multiply them in this fashion, you get the identity. Multiply them in this fashion, you get the identity as well. So that is the proof of this fact. And you can see now why we had to put the b inverse on the left and the a inverse on the right. It's so that when you go to multiply them, the b inverse and the b are right side by side, so you can actually do this cancellation and say that that product's equal to the identity. And then similarly, when you go to multiply it in this fashion, the a inverse and the a are right next to each other. If you tried to put a inverse as the factor on the left and b inverse as the factor on the right, and then try to do these calculations, you'd find that they don't work. Okay, so that's the notion of matrix inverses. They're very useful, and we'll encounter them very frequently through the rest of this course.